energy and power. So as a starter question, we're going to think about what is energy? It's something we've talked about since year 7, probably earlier. But what actually is it? I mean, we could talk about, the different types of energy, kinetic energy, potential energy, elastic energy, things like that. But if I actually to describe what it is, what actually is it? Well, that's sort of what we're going to start off with. So in our topic, we're going to look at work and energy in this lesson. Next lesson, we're going to look at kinetic and potential energy, then power, and then energy and efficiency. So our spec reference then. We need to look at work, energy, and power. So energy transferred, some quantitative examples, efficiency, and then the principle of conservation of energy, including gravitational potential energy and kinetic energy, and applying that to various examples. This lesson will define energy, describe how we measure it, discuss whether it ever disappears, and define what work done is. So, I asked you, what is energy? Energy is needed to make things happen. We could start with that as our basic sentence. If something doesn't have energy, it can't happen. So it's a way of sort of saying, is something permitted to happen or not? It cannot be created or destroyed. If there's a certain amount of energy before something happens, there's going to be the same amount of energy afterwards as the total in the system. But that energy can be transferred from one form to a different form. It can be transferred from between the different types of energy. Does that really tell us what it is? Possibly it does. Energy is needed to make things happen. It's a way of saying whether something's permitted. That could be a good enough definition. What I really just want to do is just talk a little bit about how this physicist, Richard Feynman, defined what energy was. So there's a whole series of lectures that he did at Caltech University in America, which have been published as like a series of books. Very, very sort of famous series of lectures. So I'll read it out. There is a fact, or if you wish, a law governing all natural phenomena that are known to date. There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy. It states that there is a certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes. That is a most abstract idea, because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It's just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate a number again, it is the same. Something like the bishop on a red square, and after a number of moves, details unknown, it is still on some red square. It is a law of this nature. Since it's an abstract idea, we shall illustrate it by the meaning of it by an analogy. Imagine a child who has blocks which are absolutely indestructible and cannot be divided into pieces. Each is the same as the other. Let us suppose that he has 28 blocks. His mother puts him with his 28 blocks into a room at the beginning of the day. At the end of the day, being curious, she counts the blocks very carefully and discovers a phenomenal law. No matter what he does with the blocks, there are always 28 remaining. This continues for a number of days, until one day there are only 27 blocks. But a little investigating shows that there is one under the rug. She must look everywhere to be sure that the number of blocks has not changed. One day, however, the number appears to change. There are only 26 blocks. Careful investigation indicates that the window was open, and upon looking outside, the other 2 blocks are found. Another day, careful count indicates there are 30 blocks. This causes considerable consternation, until it is realised that Bruce came to visit, bringing his blocks with him, and he left a few at Dennis's house. After she has disposed of the extra blocks, she closes the window, does not let Bruce in, and everything is going along all right, until one time she counts and finds only 25 blocks. However, there is a box in the room, a toy box, and the mother goes to open the toy box, but the boy says, "No, do not open my toy box," and screams. Mother is not allowed to open the toy box. Being extremely curious and somewhat ingenious, she invents a scheme. She knows that each block weighs 3 ounces, so she weighs the box at a time. When she sees 28 blocks, and it weighs 16 ounces. The next time she wishes to check, she weighs the box again, subtracts 16 ounces, and divides by 3. She discovers the following: that she can find the weight of the box minus the weight of the bricks. There appear to be some new deviations, but a careful study indicates that dirty water in the bathtub is changing its level. The child is throwing the blocks into the water, and she cannot see them because it is so dirty, but she can find out how many blocks are in the water by adding another term to a formula. Since the original height of the water is 6 inches, each block raises the water by a quarter of an inch, and he keeps going like that. In the gradual increase in complexity of her world, she finds a whole series of terms representing ways of calculating how many blocks are in places where she is not allowed to look. As a result, she finds a complex formula, a quantity which has to be computed, which always stays the same in her situation. So what's the analogy of this to conservation of energy? The most remarkable aspect we must be abstracted from this picture is there are no blocks. Take away the first terms in those two equations that are on the screen. We find ourselves calculating more or less abstract things. The analogy has the following points. First, when we are calculating energy, sometimes some of it leaves the system and goes away, and sometimes some comes in. In order to verify the conservation of energy, we must be careful that we do not put any in or take any out. Second, the energy has a large number of different forms, and there is a formula for each one. For example, gravitational energy, kinetic energy, heat energy, elastic energy, electrical energy, chemical energy, radiant energy, nuclear energy, mass energy. If we total up the formulas for each of these contributions, it will not change except for the energy going in and out. It's important to realise that in physics today we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs of a definite amount. It is not that way. However, there are formulas for calculating some numerical quantity, and when we add it all together, it gives 28, always the same number, not necessarily 28. It was an abstract thing in that it does not tell us the mechanism or the reasons for the various formulas. This is what I'm trying to describe, that energy is quite hard to describe what it is. It's something we can calculate, but we're not really very far forwards with saying what it actually is. So energy can be stored in different ways and transferred from star to star. The 4 ways it could be transferred: by heating, by waves, by an electric current, and when a force moves an object. Examples of energy stores, we had some on the previous page. Internal energy, so the energy stored by the particles of something. Kinetic energy, movement energy. Gravitational potential energy, the energy of something that's held high in the air. Elastic potential energy, the energy of something stretched. Thermal energy, the energy of hot things. Magnetic energy, the energy between two things that are magnetic. Could we give an example for each of those? I really hope we could. So what about internal energy? The food we eat gives us the energy to do things. So if we did not eat food, we would not be able to move around. It is a way of saying whether things are permitted or not. Kinetic energy. If we jumped on a bike and started cycling, that is kinetic energy. If we held a ball high in the air, right before dropping it, it has got gravitational potential energy. Why the word potential? Because it's got potential to be released. Same with elastic potential energy. If we stretch an elastic band, when we release it, that energy is released. When we release the ball, that energy is released. Thermal energy, hot cup of tea, magnetic energy, between two magnets. Straightforwards, right? How would we increase the amount of energy stored on each one? Well, we'd have more food, we'd move the cyclist faster, the ball could be held higher, we could stretch the elastic band more, we could make the cup of tea hotter, or we could use stronger magnets. So in each way, it's usually straightforward to see what each type of energy is, where it would be stored, and how to increase that store of energy. Energy is measured in joules. Symbol for that is a capital J. 1 joule is the energy needed to raise 1 newton in weight through 1 metre. So if I take a small bag of sugar and lift it from the ground to about waist height, that is 1 joule's worth of energy. When the energy transferred is in a closed system, the total amount of energy in the system before and after the transfer does not change. So that's what we're on about. We need to look at everywhere. If we consider the whole system where none of the energy is escaping, the energy before and the energy after does not change. So that might be, we have to look at the food that we eat. When we look at the food to start off with, we can measure the amount of energy in that. Look on the back of the packet maybe. Let's find out how many calories. Afterwards, that energy in the food will all have been changed into different forms. It may have been transferred into movement energy as we ride the bicycle. It may have been transferred into heat energy as our muscles get hot when they work. It may have been transferred into sound energy as we're breathing. If we add all of those forms at the end up, they should equal the amount of energy in the food. This is the principle of conservation of energy. Energy cannot be created or destroyed, only converted from one form to another. What about work? Work is done when force moves an object. As a result, energy is transferred. So when a force moves something, that needs energy, and we call that work done. The amount of work done is equal to the energy transferred. They're the same thing, they're just different words for it. So they're both measured in joules. We'll measure the amount of work done. We can calculate it by doing work done equals force times distance moved in the direction of the force. That is a vector, that's S for displacement. W equals Fs. So, for instance, if I were walking along a level floor, I'm not doing any work against gravity because I'm not trying to move my weight up or down. The line of action of weight is down towards the centre of the earth, and I'm moving at a right angle to that. So I'm not doing any work against gravity. If I were to start walking up a hill, I would be doing work against gravity because I've got to move my mass higher in the gravitational field. I am doing work against friction when I walk across a horizontal floor. So if the force and movement are at 90 degrees, as in the force is perpendicular to the direction of motion, there is no work done. The same as if there is no motion, there is no work done. If the force acts at an angle, so say the hill that I'm walking up is at an angle theta, then we would find that work done is force times distance moved times by cos of theta, the cos of the angle between the line of action of the force and the direction of movement. So we could see that if the angle was 90, cos of theta would go to 1, perpendicular, it's the maximum work done. If the angle was 0, they were parallel. If work done, I'll start again. If the cos of the angle was 90, it would go to 0. If they are perpendicular, no work is done. If the angle was 0, they were parallel. Cos of theta goes to 1, work done is force times distance. It's at a maximum. We could plot a graph of force against distance. In the top graph there, the force is constant from a distance equals 0 to distance equals s. In the bottom graph, the force changes with distance. Either way, in each graph we calculate the area beneath that to work out the work done. So the top graph, very straightforward. Find the area of the shape. It's a rectangle, we do one side times the other side, force times distance, F times S. Well, that's our formula, isn't it? In the bottom graph, slightly more complicated, we could divide it into strips and work out the area of each strip. That's something like integrating for the mathematicians. If we were doing it in the exam, the other way that they could ask you to do it is counting the squares underneath. So you can do a good estimate by counting how many squares and working what each square is worth. So, as a plenary question, I'll ask the same as the starter. What is energy? I hope it's a little bit more clear. If it's a little bit less clear, we could go back to another quote of Richard Feynman's, which is the shut up and calculate one that I mentioned when we did quantum physics. There's lots of bits of physics where you could dive in very deep with the philosophy, when really what we want to be able to do is calculate what's going on. Given these initial conditions, what's going to happen next? Do we need to know what energy is to be able to do that? No, we don't. What we need to know is the law of conservation of energy. Energy can't be created or destroyed, only changed from one form to another. That is our important thing. So the rest of this topic will look at energy transfers from one place to another and the different ways we can calculate it.